Hey folks, welcome back to part 4 of my robot arm build series. So in this video we're going to talk about the inverse kinematic model that I'm going to be implementing for this robot arm. So that sounds scary and confusing, and I have to give you some forewarning. There is going to be a fairly large segment of this video which is basically just going to be me explaining some maths. So that's not everyone's bag, but if you want to stick around to watch that, go right ahead. And if you don't, when the maths part's about to start, I'll throw a little timestamp up so you can skip on past the maths part if you don't want to watch it and just want to watch the end result of all the maths. So first things first, actually, I was in the last video, you might have noticed I was having some trouble with some of the joints slipping for the robot. And basically the main problem was these little pins in here that are basically the axles that all the axes run on. They're very hard stainless steel shafts, and they're very, very smooth. And the only way that I was basically grabbing them was these flanges have set screws, I was just tightening down against that, which isn't hugely robust. So basically if there was any amount of load on it, it would just slip around that. So I got around that by grinding some flats onto the surfaces to make the ends of these shafts square, basically, and now it grabs on much tighter, it doesn't slip anymore, so that's good. Okay, so back to the inverse kinematic model. So it's basically just a fancy way of saying that I want to tell the robot exactly where the end point of the effector should be. I know the end effector is here, but I'm pointing to here because you'll see when I go through the maths that this is the point basically that I'm going to be positioning. So you saw before when I'd moved the thumbsticks of the robot that I was just individually moving each of the axes, which is essentially the thumbstick position was directly controlling the angle of these servos, which is fine, it works, but if for this small robot where I only have a very limited number of axes, it's a little cumbersome to move the robot around, but it can be done by hand. But imagine if you had 6 or many more axes, it wouldn't be that easy to do by hand. And so what you would like to be able to do instead is say give an XY coordinate in space for where a point on the arm should be, and the software that's running on the robot should be able to figure out all those angles. So that is, I tell this end effector point, say that it's starting here, I tell it that I want it to be over here, so it knows that it needs to move that axis a little bit that way and this axis a little bit that way to get to that point, and that both of them move basically at the same time to achieve that motion. So with that, you can imagine, say if I'm using a thumbstick, that I can map one up and down on the thumbstick to be up and down here, and I could move assign left and right on the thumbstick to be back and forward here, which is fairly simple to control then. And also when you work out all the maths, you could have as many different axes in here as you want. So with all that said, I think it's time to go ahead and talk a little bit about the maths. So don't worry, you can skip on ahead and you can have a look at the end result. Okay, we are going to do some maths. So if you're not interested in maths, you can skip ahead a few minutes and skip past my explanation. But what I'm going to do is I'm going to draw a diagram, a basic diagram of my robot arm, and then what we're going to use that as our reference to derive a very, very basic inverse kinematic model for the arm. So there's a couple of things off the bat I want to say. I'm not an expert in this. The model that I'm deriving here is a highly simplified model that works with some of the some of the specific geometry of the arm that I have, and also I'm simplifying the model as well. I'm removing one of the joints, so I'm actually removing the wrist joint from the model, so I'm going to deal with that a little bit differently. But I just wanted to go through, give you guys the idea about how you can approach this type of thing and some of the maths that goes behind it. So with that said, let's start off with basic sketch of our robot arm. So this is just our base plane, and from here we've got the bottom part of the arm, and we've got the top part of the arm. So again, we're leaving out the wrist part. So we have our joints there. That's the end point in this model, and then this is the base point. So we'll call this point 0, 0, which is our origin, so that's our base point, and we'll call this point, which is the end where we want the robot arm to be, X and Y. So I'm leaving them as X and Y because these are basically going to be the inputs. So this is what we will tell our robot where we want it to go. We'll say, I want your end effector position to be at the point X, Y. Okay, so with this now, we need to define basically a couple of things. So we know we want the end effector's coordinates to be X and Y, but we only have two things that we can modify. So there's a couple of angles in here that we can change, which is basically rotating those servos. So one angle we can modify is this internal angle here, which I'm going to call beta. And then we can also change, so there's two angles either side here. Just for reference, I'm going to use this angle, and I'm going to call this one theta. So those are our two reference angles we can do. So if we move the servo down to the very bottom, we can change the angle theta. And if we move the servo in the middle of the arm, we can change the angle beta. So moving both of those angles will change the XY coordinate at the end here. So what we want to do is we don't want to do it, say, set this angle, then set this angle, and then see what that works out to be. We want to provide the X and Y, and then know what angles to set these to. So now we have to do a little bit of maths. So first thing I'm going to do is I'm going to draw a dotted line along here. I'm going to call this L. So L, it forms the base of a triangle here, which we'll deal with in a minute, but it also forms the hypotenuse of another right angle triangle here. So this right angle triangle is essentially between the 0, 0 point and the XY point. The hypotenuse is L, so we'll call this side, which is in the x-axis, we'll call that X because that's going to be the length of it, and then this one is also going to be Y. So first thing we can do, using the distance formula for a line, is we can say that the length of L is going to equal the square root of x squared plus y squared. So this would be, if you were to look at the full formula, you've got x1, y1, x2, and y2. It basically simplifies down to this because we know that we're working from the origin, so those 2 points are going to be 0. So essentially, it works out as this. So we're just going to keep that for the moment, and then we're going to move on. So let's come to our triangle now that has this base length of L. So one specific case, and this is one of the simplifications that I wanted to talk about, we had here that these two lengths, I'm going to call them A, they're the same. So the way I'm setting that up is basically the two arms that I made are identical. So about these pivot points that I have here, the arms are roughly about the same. So that simplifies this triangle a lot in that if you have these two sides are the same, and we know the length of this one, we can also say that these two angles are going to be the same. So we're going to call these alpha. So you're probably seeing where I'm going now, that we've got a triangle with the three angles all noted down, and we happen to know the two of them are the same. So with that, we can start to do a little bit of maths to work out what the angle beta should be based on knowing alpha. So I'm going to draw another line. So this is a line that's going to drop down to here, and it's going to be perpendicular there. So you're now seeing we've got two little right angle triangles inside the larger triangle. So with this, we can now use some of our trigonometric identities to work out an expression for the angle alpha. So we know one side, we have the angle sitting here, and we have the entire length of this base. But because of what I said earlier, that we know these angles are the same and we know that these lengths are the same, I know that this length here is half of L. So with that in mind, I can write out an expression for the angle alpha. So in this case, I know that the cosine of alpha is going to equal to L over 2 all over A. So that is the adjacent over the hypotenuse is equal to the cosine of the angle. So this is L over 2, because I know that this perpendicular line cuts the entire thing in half. So I can say that alpha is going to equal to the inverse cos of L over 2 all over A. Of course, we know A is a constant because that's the length of the arm. And then we can compute L because we know what the x and y coordinates that we want this to be are. So therefore, we have a fully qualified expression for the angle alpha. So with that in mind, we can also now very quickly work out the expression for beta. So it's a triangle, so all of the internal angles must sum up to 180 degrees. We know two of these, which are alpha, so therefore we can say that beta is going to equal 180 minus 2 times alpha. So again, we've gone through our derivation. We have a fully qualified expression for alpha, and we now have a fully qualified expression for beta. So this is helpful. So we now know the internal angles of this triangle. But the only thing we don't know is this angle theta, which essentially is so we know the relationship between the upper and lower arm, but we don't know the relationship between the lower arm and our base plane. So we need to work that out. So we have our expression for alpha, and theta is what we want. So we're just missing one piece of information, and that's this angle here, which I'm going to call phi. So to calculate phi is actually pretty easy as well, because we know the xy position, we have this length L, and we know that we start at the origin. The angle phi is actually just a really simple, another really simple trigonometric identity, which is going to be that the tan of phi is equal to is going to be equal to x over y, which is the tangent of the angle is equal to the opposite over the adjacent. So that's x over y. So therefore the angle theta, or phi, sorry, is going to equal to the inverse tan of x over y, which again, x and y are inputs, so we know those values. So we have another fully qualified expression for phi. So now, final thing we need to do is we need to work out theta. Because this is a straight line across here, we have the three angles, we know two of the values. So therefore, theta is going to equal to 180 minus alpha minus phi. And that's it. That's all of our angles worked out. So with these equations, we can fully set the final position of our arm. So two of these are kind of intermediary. It depends on how you look at it, but two of them are kind of intermediary. For example, the alphas, we're not going to be outputting the alpha angle as such, and the same with the phi angle. They're kind of, they're facts, so we can't really change them. What we'll be modifying is this theta angle really, and we'll be modifying the beta angle. So the way I'll do this in code now is I'll take as a function input the x and y values, and using those inputs to the function, I'll work out all the intermediary angles, and then I'll figure out what this theta angle should be, and I'll figure out what the beta angle should be. So the theta angle, then I will use essentially this. If you imagine in real life, this will be, the arm will be at a set angle already, and I'll be wanting to move that by a certain amount. So essentially theta will be used to work out by how much I need to rotate the servo to make the angle what I actually want it to be. And then that'll be the same will apply for the beta angle. So essentially those are the only two sort of output angles that I actually need. But I have used these intermediary angles to fill in all the blanks and make it work. I hope I didn't skip over too many steps there. I did just jump into some of these trigonometric identities. They're not crazy complicated, but you have to know them in order to know them, which is a very silly statement, but it's kind of one of the facts of it. So yeah, hope that was easy enough to follow. But basically, this is what I'll be implementing in my code to make my robot move the way I want it to move. Okay, we're back. Hopefully you enjoyed that maths. If you stayed and watched the maths, fair play. If you didn't, that's alright. Still just happy to have you. Okay, so we'll do a quick demo of what all that maths meant and how what it ends up looking like when it's implemented. So first thing I should say though, actually before that, is that I'd never, before starting this, I'd never actually looked at an inverse kinematic model before. I knew the rough concept of it. I'd seen it especially mentioned in some of James Bruton's very good robotics videos on YouTube. I'd never actually done it before, so on my last video when I posted it, threw a link up on Reddit and asked for some people's advice on r/robotics, and got a load of great feedback there for different resources to use to learn inverse kinematics. So having a rough idea of how it should work in my head, I was able to go through those resources and confirm some of my thinking and learn a little bit more about it. So I'm not going to throw the individual links to the different resources in, because there was a whole bunch of them, but I'll throw a link in the description to the Reddit thread where you can go down through it and see in the comments there's a whole load of different stuff there. So also a big thanks to all the guys on Reddit who linked to resources. You guys are awesome. Okay, so we'll do a little demo now. Also the motion isn't perfectly smooth. There's a lot of backlash in the servos, and the servos obviously aren't a perfect way of doing this. And mechanically there's it's not the best thing in the world, but it does work. So keep that in mind. Also, I eyeballed, there's reference angles and reference lengths and stuff that you need to put into the formula to make them work. I basically eyeballed all of those. So let's turn it on anyway and see what it does. Okay, so this is our set 0 position. So from here, if I move the stick up, hopefully, yeah, it moves up in a relatively straight line. Same if I move it down, and then if I push forward and backwards. And then of course I can mix that together by moving all of the axes at the same time, which is pretty cool. So actually one thing to note as well is the end effector here. This isn't part of that inverse kinematic model. It just basically I have it set to be mimicking one of the internal angles from the calculation, so it just sort of moves around a little bit. I might play with that a little bit because I think I'd like it to be always sort of perpendicular so that it can move. It'll be sort of like a chicken head, just staying in one place as it moves around, same parallel to the ground. But yeah, that's essentially it. When you move it up, the two axes move to keep that position in pretty much a straight line, and then the same when I go out and back, and then yeah, mix them together. So yeah, that's the basics of an inverse kinematic model. Turn it off, it won't support its own weight. Yeah, that's pretty much it for what the implementation of that looks like. I'm very close, I think, nearing the end of this project as such. At the moment I've just got this one thumbstick controlling those axes, which is great. I don't have the end effector wired up yet or connected up. As you saw in previous videos, I do have the stepper working. It's just this piece of code doesn't have that stuff running on it. So I think the next thing I'm going to do, which will pretty much finish it off, is I'm going to maybe make this push button open and close the grabber, and just wire the stepper movement up to the axis, one of the axes on this thumbstick. I think that'll be pretty much it, really. So yeah, with all that said, I should also be able to use the same maths that's taking this XY coordinate to input and use it to program the robot to do a series of motions. So I should be able to program it to move down, pick up an object, move up, drop the object, that kind of thing. So I might make that as a goal for maybe the next video or something like that, to have the robot actually do something like that, move, pick up an object, move somewhere else, drop the object, and go back. Maybe like a useless machine that picks up a ping pong ball and drops it and keeps doing the same thing over and over again. That would be, I think, a cool goal to have, to be able to do with this little robot. But for now, that's pretty much it. So I hope you learned a little bit about inverse kinematics. I hope for those of you interested in the maths, you liked it. Give me some feedback as well if you know maths well and stuff, and you want to point out if I made any stupid mistakes. I do have to say that it wasn't a fully in-depth treatment of it, but it was a basic kind of geometric overview of how you might approach this kind of thing. So yeah, hope you liked that one. Like, subscribe, share the video. If you'd like to help support the work I'm doing, you can find a link in the description to my Patreon. Yeah, so I'll see you guys in the next one, and as always, thanks for watching.